Hello, have you ever heard of the cFlow? cFlow is an EU-funded H2020 international project aiming at developing an integrated photonic platform for coherent free-space optical communications established in the mid-infrared range. The photonic platform developed in the cFlow project operates in the long wavelength infrared transparency window of the atmosphere, covering the wavelengths ranging from 8 to 14 micrometer, which has been identified as optimal window by numerical model of the atmospheric transmissions. The unipolar quantum technology operating in this particular transmission window, which currently remains largely untapped, offer a vast potential for high-end photonics applications since it combines two main advantages with respect to other competing FSO technologies established in the millimeter terahertz or in the 1.55 micrometer telecom domains, an optical carrier at 30 terahertz for high-capacity and long-reach communication links, and a channel that is less sensitive and fluctuating in adverse atmospheric conditions. The whole cFlow platform is composed by two main parts, an emitter and a receiver photonic integrated circuits, each of them integrating basic building blocks developed in the framework of the project and based on quantum cascade technology. This artistic illustration shows on the left the concept for the emitter module, consisting of a distributed feedback quantum cascade laser, a high-frequency waveguide Stark modulator, and a semiconductor optical amplifier. On the right side, the corresponding heterodyne receiver module is presented. Key components for the receiver module are a local oscillator, an SOA preamplifier, a plasmonic waveguide for beam routing and combining, and a photomixer. To achieve this ambitious goal, the cFlow Consortium federates 7 European partners from academia, research and development labs, and industry. Terrestrial FSO links, in particular those close to ground, may take advantage of the reduced atmospheric impact offered by operating in the long-wave infrared. The cFlow design laser wavelength was set to 9.124 micrometer within an atmospheric transmission window suitable for broadband communication. Impact of fog and turbulence was examined in the project. An advantage for the long-wave infrared in comparison to the short-wave infrared was found only in certain fog conditions, depending on the aerosol size distribution in the fog. A more distinct advantage was found to be the reduced level of distortions caused by turbulence. In particular, a coherent optical link will benefit from potentially higher receiver efficiency and from relieved alignment requirements. A framework of typical component requirements arising from the links considered were worked out to provide guiding to the cFlow development. Link budgets were also calculated for the purpose of comparison with shortwave infrared alternatives. Target specifications for the project were developed based on requirements for a coherent link operating over 5 km at 10 gigabits per second. A laser output power of 1 watt was set as a design value for the transmitter. For the receiver, a relatively challenging design value for the quantum efficiency of the optical detector of 0.1 in combination with a local oscillator power of 8 milliwatts was set. In this project, we have successfully demonstrated a single-mode quantum cascade laser emitting in the long-wave infrared region, achieving an optical power output of 50 milliwatts in continuous wave mode at room temperature. The laser is emitting at the targeting wavelength of 9.2 micrometer, which can be slightly tuned with the injected current. The figure on the right illustrates the laser's spectra, showing its single-mode operation with a high side mode suppression ratio of 30 decibel, typical of distributed feedback lasers. For free-space optical communications over several kilometers, higher optical power is required. To address this challenge, we have developed a configuration where an amplifier is monolithically integrated with the DFB laser. This integrated configuration is referred to as a Master Oscillator Power Amplifier, or MOPA. In the first figure, the amplifier section is located at the front and is bounded at the right of the submount, while the DFB laser is placed on a separate contact, allowing independent biasing of each section. In the second figure, we present the power current characterization of MOPAs and DFB lasers in pulsed mode operation at room temperature. The red curve represents the configuration that achieves the highest optical power, reaching a peak power of 1.2 watt. The green curve represents the characteristics of a DFB laser, and the blue curve shows AMOPA of the same geometry. Our results demonstrate that implementing the semiconductor optical amplifier section increases the optical power by 7.5 decibel. The last figure displays the spectrum of the MOPA structure for different levels of current injected into the amplifier both below and above its self-lacing threshold. As seen, the MOPA emission remains single-mode with a high side-mode suppression ratio in all scenarios, even when the SOA section is self-lacing. This indicates that the DFB seed mode is predominant on the SOA Fabry-Perot modes in this specific regime. This phenomenon is advantageous because the SOA is limited by saturation effects, which constrain the achievable amplifier ratio. Therefore, we can enable the amplifier to lace, increasing optical power while maintaining single-mode operation. One of the key functionalities to be implemented on a free-space optical communication system is encoding information on an optical signal through amplitude or phase modulation. In the framework of cFlow 3.5 Lab developed an integrated version of an optical modulator based on the Stark shift effect in asymmetric coupled quantum wells operating around 9.1 micrometer. Different generation of modulators have been fabricated. In the image below, an example of an epi-up version with 3 sections in a straight waveguide configuration. By appropriately biasing the central active section, the transmission of the modulator can be tuned in and out of resonance. A modulation depth of 7.5 decibel at 9.1 micrometer can be achieved for a 100 micrometer long modulator, and a bias excursion between -2 volt and +4.5 volt, as shown by the red curve of the central figure. Through Kramers-Kerr-Nigg relationships, it is also possible to retrieve the phase variation achievable with the current design, which can be estimated to be roughly 120 degrees between -3 volt and 0 volt, around 9.1 micrometer. The experimental bandwidth of the component has been by using a microwave rectification technique. A -3 decibel bandwidth of around 1.4 GHz is obtained. It is worth noticing that the main limitation to the current design comes from parasitic capacitance associated to the coplanar waveguide used to inject the RF signal. 3.5 Lab also developed a more compact version of the waveguide Stark modulator. This version, based on a double-trenched configuration, is flip-chip integrated by CSEM onto a carrier, together with the DFB Quantum Cascade Laser and the semiconductor optical amplifier developed by MirSense, submount to realize the final cFlow transceiver PIC. Given the absence of coplanar waveguide, this improved architecture is expected to provide significantly higher bandwidth than the previous one. Alongside the development of plasmonic waveguides led by TUW, which will be presented later in this video, 3.5 Lab worked on a complementary approach based on multimode interferometers for beam routing, splitting, and combining across the integrated photonic platform. Different configurations with a variable number of inputs and outputs have been developed. Here, a 2x2 component used for balanced heterodyne detection is shown. Splitting ratio of 50 around 8% from 9 micrometer to 9.4 micrometer, and phase relations between the two outputs close to the theoretical value of 180 degrees with a measured phase error below 10 degrees through a wavelength range spanning from 9 micrometer to 9.3 micrometer have been measured. These results are in excellent agreement with the theoretical performance achievable by this kind of device. Moreover, this component shows a relatively broad wavelength range of operation spanning between 9.0 up to around 9.4 micrometer, making it an interesting candidate to be integrated onto a monolithic photonic platform. A more advanced concept based on a 2x4 90 degrees hybrid MMI has also been realized. This version is adapted for more complex, coherent modulation formats. Fair overall performance has been achieved for this first generation of devices operating in the LWIR range. As expected, this device shows 90 degrees phase shifts between the 4 outputs, with phase errors smaller than 25 degrees in the 9.1 micrometer to 9.4 micrometer wavelength. On the same wavelength range, the measured common mode rejection ratio for the in-phase and quadrature channels is below -10 decibel. Quantum Cascade detectors based on ridge waveguide configuration and operating in the LWIR atmospheric window have also been developed by 35 Lab. Experimental photo response at room temperature has been achieved with a peak value of 140 megawatt at 9.5 micrometer. Further development of components includes optimized RF design for high-speed operation. We collected resources and manpowers from ENS Mearsense and KTH and set up a system-level transmission demonstration testbed. We used directly modulated QCL from Mearsense as the signal source and employed two different detectors, namely a QCD and a QWIP at the receiver. The QCL is bonded and mounted for high-frequency purposes. One can see the spectra of the QCL at different bias current, and the 3 decibel bandwidth was measured to be around 10 gigahertz. And both detectors are metamaterial patterned to enhance bandwidth and responsivity. For the detector and their spectra are shown in the figure. The QCD offers slightly broader bandwidth and smoother frequency roll-off after 10 gigahertz than the QWIP, however, with relatively lower responsivity. For transmission, an arbitrary waveform generator of 50 gigasample per second was used to generate the NRZ and pulse amplitude modulation signals. And a 80 gigasample per second real-time storage oscilloscope was used to capture the received signal and convert it back to the digital domain. Standard digital signal processing algorithms were developed and used at both the transmitter and receiver for signal generation and demodulation. The transmission results are shown in this slide. We showed different combinations of transmitter and detector as well as different modulation formats. The left figure shows the measured bit error rate curves at the highest achievable speed for both NRZ and 4-level pulse amplitude modulation signals. Limited by the responsivity of the QCD, the received signal has insufficient signal-to-noise ratio to achieve a speed as high as with the QWIP detector. The next figure shows the bit error rate performance when using the QWIP with NRZ signaling. One can see that we achieved 55 gigabit per second below the hard decision FAC limit and achieved up to 65 gigabit per second below the 20% overhead soft decision FFEC limit. Finally, the last figure shows the bit error rate performance when using QWIP detector with PAM4 signals and highest achievable data rates below the hard decision and soft decision FLIC limits were 60 and 70 gigabit per second, respectively. We have realized an amplitude modulator exploiting a system of tunnel-coupled asymmetric quantum wells, as shown in the top left panel. The figure shows the conduction band profile under applied electric field and the square moduli of the relevant wave functions plotted at the corresponding energy. As the barycenter of the wave functions associated with the ground and first excited state of the system are mostly localized in 2 different quantum wells, the energy separation between the corresponding states varies as a function of the electric field. As a consequence, the absorption spectrum, shown in the lower panel on the left, has a linear shift in energy with the applied voltage. For a fixed laser emission energy, the light transmitted through the modulator is absorbed, with an absorption coefficient depending on the applied voltage. In order to reach high bitrate, the modulator has been processed in a MESA geometry, as shown in the inset of the right panel. The MESA is connected through an air bridge to a coplanar waveguide and finally to ARF connector. The measured bandwidth of the device depends on the size of the MESA and can reach 30 GHz. Data transmission is realized by using a quantum cascade laser at 9 micrometer wavelength and antenna metamaterial detector and modulator, operating in reflection. The modulator writes the signal onto the 9 micrometer carrier, and the modulated light is detected by a quantum cascade detector. The 3 devices are unipolar and operate at room temperature. The metamaterial architecture used for the detector and the modulator is presented on the scanning microscope image shown on the bottom left. The absorbing region is embedded within an array of metallic stripes, connected through an air bridge to a coplanar waveguide. Compared to the previously presented message geometry, the metamaterial architecture allows reducing the device capacitance, resulting in an improved bandwidth and an easier optical alignment, as the modulator and the detector are used in reflection rather than in transmission. The panel on the right presents the eye diagram of the data transmission experiment obtained at 25 gigabits per second, with a bit error rate of 0.1%. Within the cFlow project, novel plasmonic-based mid-infrared integration concepts were developed and tested. The integration of fully tailored germanium ridges onto gold layers enabled the realization of broadband, low-loss waveguides that cover a full spectral octave from 5.6 to 11.2 micrometer wavelength. This includes the cFlow target wavelength of 9.12 micrometer in the long-wave infrared range, suitable for free space telecommunication experiments. For enabling complex photonic integrated circuits, beam guiding and directing along the chip surface is a crucial characteristic for plasmonic waveguides. For this, a novel material class for plasmonics was unlocked within cFlow. Polyethylene, as representative of the polymer class, was selected and matured during the project to the level that it can substitute germanium and realize on chip beam guiding applications. The novel mid-infrared plasmonic concepts were eventually combined with Quantum Cascade technology to implement the most important active components of a photonic integrated circuit, namely laser and detector, on the same single chip. This work included the development of a novel long-wave infrared quantum cascade detectors with high performance at 9.12 micrometer wavelength. After testing multiple approaches with germanium and polyethylene-based plasmonic waveguides, a novel concept was established within cFlow by merging germanium plasmonics with on-chip integrated optics for guiding and directing of the light. Those integrated micromirror optics were fully designed and fabricated in-house, and thus could be optimized for the right wavelength in the dedicated application. Finally, a fully monolithic integrated long-wave infrared heterodyne receiver was realized within cFlow, containing local oscillator, semiconductor optical amplifier, plasmonic guiding section including micromirror optics, and detector on one single chip. The obtained performance characteristics of this device are very promising to conduct high-speed data transmission experiments in free space configuration in the future. Many constraints were seen in module integration. 3 optical chips had to be flip-chip bonded with a relative accuracy of less than 2 micrometer. Step bonding of the parts next to each other using a high thermal conductivity die attach without causing a short circuit is a big challenge. The envisaged high-frequency operation of up to 20 GHz provides additional constraints like need for flip-chip bonding and high-frequency compatible circuit design. Additionally, the optical chips integrated should be temperature-controlled with an accuracy of less than 1 Kelvin. Thermal management was done, and the design of the module was made based on the constraints. The substrates were manufactured using a highly complex manufacturing sequence. The substrate enables alignment and step bonding of the optical chips, and for a high-frequency signal transmission for the modulator. The optical chips are bonded with high precision on these substrates. Further, the substrate is integrated on a heat spreader and petlier to assist in temperature control of the optical chip. Finally, the parts are assembled on a water cooling plate and covered to reduce air convection. For further information, please have a look to the project website or get in touch with the cFlow project coordinator. Thank you for your attention.